Hi, my name is Priva Halpert. I'm a student at the Cooper Union School of Engineering, and I'm excited to tell you a little bit about my work with the Topper Group. So I'm going to be presenting to you today a little bit about our work on proton transfer and specifically proton transfer in ammonium fluoride nanoparticle clusters. Now, to begin with a very brief introduction into the importance of proton transfer analysis in finite clusters, we know that nanoparticle clusters in finite sizes, so existing when they're very, very small, can have very different structures and very different behaviors, characteristics than the bulk material. Now, a lot of these characteristics are dependent on the proton transfer that exists as these clusters move from a molecular to a more ionic character. And these proton transfers are actually growth dependent. And we do see trends in the growth of nanoparticle clusters as they grow. And we see trends in the proton transfer and the way that it plays out. Now, my group tends to focus on ammonium halide clusters because they are very important in understanding atmospheric conditions. And we tend to focus on studying their growth and their decay of these nanoparticle clusters. So my group has previously worked on ammonium chloride, ammonium bromide, and the image that you can see over here is some of our work on ammonium nitrates. And the growth trends that we see in those materials. Now, I'm going to be presenting to you today specifically about ammonium fluoride clusters, which are, let me move my picture a little bit down, but ammonium fluoride clusters are actually a very unique case of these ammonium halides, and that is because of the nature of the hydrogen bonding that it can exist in. So because hydrogen fluoride is such a weak acid, the proton transfer as these nanoparticles grow will actually compete with very strong hydrogen bonding between the hydrogen of the hydrogen fluoride and the nitrogen of the ammonia. So we do see a flip-flop between the completely ionic and the completely molecular motifs of these nanoparticle clusters. Now, the reason why ammonium fluoride is more unique than other ammonium halides, it's because it actually has three different motifs that ammonium fluoride can exist in. Ammonium fluoride can exist in a traditional, in which we have traditional hydrogen bonding and everything retains its original molecular form. A proton-shared type of hydrogen bonding in which one proton or more is shared between an ammonia and a fluoride between the two of them, or an ion pair conformation in which all of our protons are completely transferred to the ammonium. Now, this is very unique because other ammonium halides do not exist and do not exhibit this trend of also including a proton shared motif. And what's actually important and one of the main motivations behind this project is that since the proton transfer is actually a growth dependent trend, analyzing the growth of ammonium fluoride can actually tell us a lot about the nature of hydrogen bonding, since the ammonium fluorides will transition from traditional to ion pair hydrogen bonding by way of proton shared hydrogen bonding. Analyzing its growth as a nanoparticle can tell us a lot about the nature of proton transfer and the nature of hydrogen bonding. So to do this, this is actually a computational group. My group is a computational chemistry group. We use what's called Monte Carlo simulated annealing. If anyone's familiar with quantum chemistry, you know that a lot of calculations are done using quantum calculations, and we do a number of quantum calculations as well. But quantum calculations are very computationally expensive, especially if you're doing nanoparticles and especially if you're doing large nanoparticles. And since we are trying to see when our clusters are approximating bulk material, quantum calculations are just simply too expensive. Instead, we use a simulated annealing Monte Carlo software, which is significantly cheaper. We have our own software developed by my group called Transfer, which is available at the GitHub over here if anyone's interested. And to do this, we minimize the energy according to a modified OPLS force field. And I'm happy to answer any questions about that if anyone wants to reach out via email. But this project does rely on the transroad code and the transroad method of simulated annealing. So to turn to our proton transfer model, what we try to do is we try to analyze whether or not our ammonium fluorides will want to exist in the ion paired or in the molecular state. So to do this, we develop a proton transfer model. We're trying to identify a transition point between between the molecular conformations and the ionic conformations. So to do this, we calculate the difference in energy between the molecular and the ionic pair, and this requires a parameterization from a quantum calculation. So we do a DFT a DFT calculation of the M equals 1 cluster. And by M equals 1, I mean the cluster consisting of one ammonia and one hydrogen fluoride for the molecular conformation, or one ammonium, one fluoride for the ionic conformation. So we calculate our VPT to be 157 kilojoules per mole. And using this parameterization, we're able to identify a turnover point between where the cluster prefers to remain in its molecular motif and where the cluster prefers to remain in its ionic motif. So our model predicts this turnover to be at around 3.44. Which agrees with both experimental and previous computational data in the literature, which does point to the M equals 4 cluster to be the first cluster that exhibits complete proton transfer. So this is definitely very promising, and now we will turn to a little discussion of using our proton transfer model. But before we do that, we actually want to confirm our results and confirm that our proton transfer model is actually giving us understandable results. So we do benchmark this to quantum calculations, and our quantum calculations do also favor this turnover point at M equals 4, which agrees with that of our proton transfer model. So we find this very promising. Now, we prefer to analyze incomplete proton transfer as well, because our clusters do not necessarily have to transfer all of their protons. Instead, they might only want to transfer 1, 2, or less. Now, to do this, we want to develop a graph such as the one you can see over here, although I'll move my video. And this graph is going to display the energy of each of these clusters as we begin with k equals 0. And we continue up to k equals 14, because this is an example of the k equals 14, the M equals 14 cluster. Now, when we say k, we refer to how many protons are transferred. So for the k equals 0 cluster, there are no protons transferred, and this is a completely molecular motif, as opposed to the k equals 14 cluster, which exists with a completely ionic motif. Now, we look for the highest energy point, and we find over here for specifically the M equals 14 cluster that the k equals 13 point has the most favorable conformation, the most favorable energy, which leads us to conclude that for the M equals 14 cluster, it prefers to remain with one molecular cluster. Now, we're going to do a little bit of a structural analysis, and we will see that this favors the hexagonal prism structure, which is very significant. Now, to do this, we do a structural analysis to give you a little bit of background into the structure of ammonium fluoride. Bulk ammonium fluoride exists in a Wurtzite structure, which is a bunch of tubules of hexagons. And we do look at the structures that our transrot calculations are able to give us, and we definitely see a prevalence towards these hexagon shapes. So this is very promising to us because it's indicating that our structures are favoring the bulk material. Additionally, the bulk material has been shown to exist also in a cubic form at high pressure states, and we also find these cubic motifs present in our transrot calculation. So this is definitely very promising and indicating that our results are understandable. Now, we tried to analyze incomplete proton transfer, and to do this, we use the permutation workflow that I discussed a little bit earlier, and we develop a graph like this. Now, what this graph is showing you is at the M value, so for different sizes of this nanoparticle cluster, does the cluster favor complete proton transfer or incomplete proton transfer? So we do see that for M equals 1, 2, and 3, no proton transfer is favored, and this confirms, and this aligns with the fact that the M equals 4 cluster is the first cluster that exhibits complete proton transfer. And you can see that the M equals 5, 7, 11, and 14 cluster are those that favor incomplete proton transfer, which is very unique. So we turn our discussion to analyzing incomplete proton transfer in these specific clusters. So we analyze the structures of these incomplete transfer cases to see if our simulation and our proton transfer model is picking up correct trends. And we do see trends towards both the cubic structure and the hexagonal prism structure. So we are definitely seeing alignment with the bulk phases, which is very promising and very exciting results. And we could see that these molecular pairs are continuing to exist in these structures to favor the bulk phase material. Now, some of the future work that we hope to do is to correlate our structures and their energies to an experimental mass spectrum. To do this, we are planning to use differential interaction energies, although this is still in the works, but we are nearing completion. If anyone has any questions about that, please feel free to email me. The email is listed down here below, and we would also like to thank Uber Hassan and Anna Lamboy for guidance along this journey. Please reach out if anyone has any other questions and enjoy the rest of the lectures.